Partial derivatives. Now previously we had done derivatives of a function of one variable, so there wasn't any confusion about which variable it is that you were taking the derivative with respect to. So now that we have functions of more than one variable, we're going to specifically focus on functions of two variables. So for example, z equals f of x and y, so two inputs, one output. And so now there are two variables, right? So that means if we want to know the derivative, the rate of change of this function with respect to a variable, we have two to choose from. You have x and you have y. And for some instances, you may want to know the rate of change with respect to x, and for other instances, you may want to know the rate of change with respect to y. So since that is the case, and we can really only work with one, or are only going to be working with one variable at a time and examining the rate of change with respect to one variable at a time, we're going to call these partial derivatives because we're not finding the full derivative, right? We're not finding the full rate of change of this function, just the rate of the change of the function with respect to one variable at a time. So that's why we call these partial derivatives. So if we want to know the partial derivative of f with respect to x, the notation we're going to use is this f sub x of x and y, or notice we use z. There's another notation that is partial z over partial x. And so notice this notation kind of looks like you didn't quite complete drawing a 2 here, right? This item here and here. It is just the notation that means the partial of z with respect to x. And in this case, where x is the variable of interest, and that means we're going to hold or treat y as a constant. So basically we're going to say we're gonna sort of treat y as a constant. We're not interested in how it's changing with respect to y, so we're just gonna kind of treat it as a constant. And then x is our variable of interest when we look to find the derivative. So similarly, if I want the partial derivative with respect to y, then the notation is f sub y of x and y, or partial of z with respect to y. So in this case, our y is the variable of interest, and we treat x as constant. Okay, so there's our notation that we're going to use. We're pretty much going to be using the f sub x and f sub y notation, but I'm included the others because they do appear in books and in online and all sorts of different places. So I just wanted to note that notation as well. So basically the way that we're going to do this is we're just going to look at some examples to see how this kind of works. Okay. So here's our first example. We're dealing with the function f of xy equals x squared plus y squared. So if we look at f sub x, the partial of f with respect to x, we're going to treat x as our variable of interest, and y is going to be treated as a constant. So what I'm going to do is I'm actually going to draw the function, or write the function down here, and then I'm going to underline the fact that x is the variable of interest, and that's what we're going to treat as we normally would in terms of taking derivatives. But y, on the other hand, we're going to treat as a constant. Okay, so we treat that as a constant. So all of the rules that apply to constants, so adding a constant, subtracting a constant, multiplying by a constant, all of those rules still apply. So all the rules that we had previously. So now if we're going to do partial with respect to x of a constant times a function, then the derivative is we keep the constant and multiply by just the partial, okay, with respect to x. So what does that look like here? All right, so x is our variable of interest, so we're going to treat that, right, when these match, we treat them like we normally would for derivatives. So the derivative of x squared is 2x plus, right, using the sum and difference rule, the derivative of y squared. But if we're treating y squared as a constant, the derivative of a constant by itself, right, it has no x variable in it, therefore it doesn't vary with respect to x, therefore it has no rate of change with respect to x, and therefore its derivative is 0. And this partial derivative with respect to x is 2x. Now if we switch up and now want the partial with respect to y, so again I'm just going to rewrite, and now I'm interested in the variable y, and the variable x then is going to be treated as a constant. Now this isn't a constant times the variable y, just like previously y squared wasn't a constant times x, then the constant rule applies, right? That the derivative of a constant is 0. So to start out this derivative, the derivative of x squared, since we treat it as a constant, we're trying to find the rate of change of this function with respect to the variable y. X squared does not contain a y, so there's no rate of change, and so the rate of change is constant. It is 0. Plus, now again, when the variables match, we treat them like we normally would. So the derivative of y squared, just going to use the simple power rule, is 2y. So this partial derivative is 2y. So the partial derivative with respect to x is 2x, and the partial derivative with respect to y is 2y. Okay, so that's if we have a variable of interest plus the other variable of interest, so we're going to treat them as a constant. What if we have a constant multiple like we are talking about here? Okay. So that's what we have here in this next example. G of xy equals x squared y plus 7y minus y squared x. Okay, so I'm going to do the same thing. I'm going to write my function and underline the variable of interest. And then this is going to be a constant multiple. This is a constant, and this is a constant multiple. So here we're going to use basically the idea that the partial with respect to x with anything that deals with a y is going to be treated as a constant. And then the other part, anything dealing with an x, we're just going to find its derivative like we normally would. Okay, so here we're using a constant multiple rule. And that's what we're going to use here. All right, so constant multiple rule says I keep the y, and then I multiply by the derivative of the part with the x, because that's the variable of interest. Okay, plus, now I have 7y, which is a constant. It does not have the variable x in it, so its rate of change with respect to x, there is no rate of change because it doesn't have an x, and so therefore no rate of change means a derivative of 0. Okay, now again we have our constant multiple, so the function of y times the derivative of the variable of interest, which is 1. So we clean this up. This is 2xy minus y squared. Right? So again, we used the fact that y is being treated as a constant, and so the constant multiple rule applies. Right? We just rewrite it and then times the derivative of the part with the variable. So now if I'm going to reverse the order, now I'm interested in the derivative with respect to y, then the partial with respect to y of a function of y times a function of x is the derivative with respect to y times the function of x, because now this one is being treated as a constant, and therefore it just gets rewritten by the constant multiple rule. Okay. All right, so if I've got, let's see, x squared y plus 7y minus y squared x. So I'm going to underline y, and this is my constant, and this is my constant multiple. All right, so constant multiple rule. If I have something involving an x times something involving a y, then x squared is treated like a constant, and it just gets rewritten. And then I multiply by the derivative of the variable y. Plus, the derivative of 7y is going to be 7 minus, using the constant multiple rule, the x just gets rewritten and multiplied by the derivative of y squared, which is 2y. So cleaning this up is x squared plus 7 minus 2yx. Okay, so again, I'm going to reiterate, we're using the constant multiple rule here. So I've got the constants circled in the constant multiple rule, and in each case, right, when you're taking the derivative with respect to x, then we just need a derivative of the part with an x, and when we're taking the derivative with respect to y, then we need a derivative of the part with respect to y, and that's exactly what I've done here, right? If I go back up, focusing on the partial with respect to x, 2x was the derivative of x squared, 1 was the derivative of x. The rest of it, right, is the result of the constant multiple rule. You just rewrite. And then if I take the derivative with respect to y, then the derivative of y is 1, the derivative of 7y is 7, the derivative of y squared is 2y, and the other parts, right, are just constant multiples, so they just get rewritten. Let's try another. Okay, here's x times e to the y. So x e to the y. So again, I'm going to underline the part that has the variable of interest. The other part is the constant. So the derivative here is going to be the derivative of the variable of interest. So that's x. So that derivative is 1 times the constant multiple. So e to the y. That just gets rewritten, right? So our constant multiple rule applied there. So the end result is this is just e to the y. All right, now let's switch it up. Take the derivative with respect to y. So x e to the y. Now which part is the part with the variable? This part. This part is the constant multiple, right? So again, the rule is if it's a constant multiple, it just gets rewritten. And then we multiply by the derivative of the variable part. So the exponential rule is, right, derivative of the exponential is the exponential function times the derivative of its exponent. And so the derivative of its exponent, the derivative of y, is just 1, right? So this part is the derivative of e to the y with respect to y. So this is then x e to the y. So the derivative of x e to the y with respect to y is itself. Okay. Right, and I've got another one here for you. Okay. So throw a logarithm in here, a natural logarithm, so we can see how that is tackled. So just remember the derivative of a logarithm is derivative of inside over the inside, right? That rule still holds. Doesn't matter that I now have a function of more than one variable, that rule, that structure still works here, right? That's still what we need to do. Okay, so again, 2xy plus ln of x minus y. Variable of interest is x, so x, and then x here. This is a constant, and then this will be a constant. All right, so when the variables match, the derivative of 2x is 2. Just rewrite the constant, plus, all right, here's where our rule for the derivative of the logarithm. So derivative of the inside over the inside. So I always write the inside first, right, the bottom, the denominator. Then I'm going to worry about taking the derivative of x minus y. So the derivative of x is 1 minus the derivative of y is treated as a constant is 0, right? So it's x minus a constant, notice which is different than x times a constant. One is the constant multiple rule, the other is the difference rule. So again, I'm going to clean this up. This is 2y plus 1 over x minus y. All right, let's try the next one. 2xy plus ln of x minus y. Underline, we're dealing with just the variable y in this case, and then x and 2, they're going to be the constant and constant. All right, so constant multiple rule, we rewrite the constant times the derivative of the variable y with respect to y is 1, plus, same thing here, still a logarithm, so derivative of the inside over the inside, so I'm going to write the inside in the denominator, and then take the derivative of the inside. So the derivative of x is a constant by itself, is 0, minus the derivative of y, which is 1. So this is cleaned up, 2x plus negative 1 over x minus y, or 2x minus 1 over x minus y if you prefer. Okay, here's another. This one is going to require, right, a quotient rule. Just like before, if we see a quotient, this is going to require a quotient rule. So I'm going to do this a little bit differently than I did the others. And since this is the quotient rule, if you've done, bottom d top minus top d bottom over bottom squared, or some students use what's called the ribbon method, where you write the numerator and you write the denominator. And then my variable of interest is x. This is a constant. And I'm going to take the derivative of each right across from it. So the derivative of x plus y is 1 plus 0. The derivative of x minus y is 1 minus 0. And then what I'm going to do is use a neat little trick that will help me with the numerator. So bottom d top, bottom times the derivative of the top. So if I actually start my ribbon down here, start at the bottom, the x minus y, that's my bottom. And then it multiply by the top right, that's the d top. And then minus the top d bottom. All over the bottom squared, x minus y squared. So this is x minus y minus x minus y all over x minus y squared, which simplifies to negative 2y over x minus y quantity squared. Okay. All right, so I'm going to do the similar sort of thing down here, as I'm going to separate them. And I think this becomes helpful when doing partials, because you can really focus on the part that is the variable and the part that you're going to treat as a constant. So in this case, the derivative of x plus y with respect to y is going to be 0 plus 1, or 1. The derivative of x minus y with respect to y is going to be 0 minus 1, or negative 1. So then the derivative, start down here, times that, minus the product of the other two. So bottom d top minus top d bottom all over bottom squared. And so this is x minus y minus negative x minus y all over x minus y squared. And this ends up being x plus x, so 2x, negative x plus y, so the y's will cancel, over x minus y squared. Okay, and for good measure, I've got one more here for you, just so that we can see how the extended power rule works, or the general power rule, or chain rule, power rule form, however you want to think about it. So the first thing is we need to use our algebra and properties of radicals and exponents to rewrite the square root of x squared plus y squared as x squared plus y squared all to the 1/2 power. Then we're going to go ahead and use the general power rule, which works exactly the same way. The general power rule, or the extended power rule, is, if we're going to focus on x, but essentially it works the same, bring down the exponent, rewrite the inside, subtract 1 from the exponent, and then multiply by the derivative of the inside, right? So the derivative of x squared plus y squared. Right, there's the variable. That part's treated as a constant. So the derivative of x squared plus y squared is 2x. And if we clean that up, you've got 1/2 times 2x is just x. Negative a half means it gets pushed to the denominator, and a 1/2 power means a radical square root. Similarly, if I want the derivative with respect to y, same thing applies, right? I'm going to do the extended power rule. Bring the 1/2 down, subtract 1 from the exponent, and then multiply by the derivative of the inside part. So x squared plus y squared. This time y is the variable of interest, and x is the constant. So 0 plus 2y, or in other words, just 2y. So again, 1/2 times 2y is y over square root of x squared plus y squared. So hopefully this is enough, these are enough examples to get you going and be able to complete any other partial derivative problems that you may be faced with.